Grade 12, here's the answers to our magnetism test that you guys did very well on. I'm just going to quickly go through the answers. The first question where we're looking at calculating the force on a current carrying wire, you use this equation, all right, for the current carrying wire in a magnetic field. The drawing showed the direction of the force, so you just plug the numbers in for the magnetic field strength. 200 millitesla is 0.2 Tesla. I is 1.5, my length is 0.1. And when you put that in, you'll get 0.03 newtons. Here is the drawing of the magnetic field. As long as I saw that everything was symmetrical, you got your grades. Okay, and remember, magnetic field goes from north to south. This question caused a lot of problems for people, and I can understand why. You have to really be careful when you're following the current in this coil. So the current was going up behind and then down in front. So if I use my right-hand rule, and my thumb points down on that wire, my fingers will coil in the inside. So these red arrows show my fingers showing the direction inside of the magnetic field, which then wraps around outside. Okay, on the outside, the magnetic field is going to go in this direction. So that's the North Pole, and that is the South Pole. So please take a look at your drawings and try this again with the right-hand rule to make sure that you can do this. Okay. All right, the next question was to draw the path of an electron in a magnetic field. The X's mean that the magnetic field is going into the page. And if you used the Fleming's left-hand rule for a positive charge, the positive charge should go up. But remember, electrons are opposite. So whatever the positive charge would do, the electron will do opposite. So it goes down. And why does it make a circular pattern? Well, because the magnetic force is always perpendicular to the motion, according to the left-hand rule. And any force that's perpendicular always to the motion is known as a centripetal force. All right. In this question, to calculate the radius of curvature, you look at the magnetic force, which for a charged particle is BQV, is going to be equal to mv squared over r, something we practiced in class. And then when you rearrange the equation, r is equal to mv over bq because one of these v's cancel out. And then your r is going to be quite large due to the high velocity of that electron. All right, in the next question, it asks what should be the direction of the magnetic field so that the electron can go up. And a lot of us got confused on how to draw that. Okay, and this is what I was testing to see if you actually did a lot of problems that showed this formalism. Okay, so if I see these dots on a page, that means that the magnetic field is coming out of the page. X's mean it's going in, the dots mean it's coming out. And if you use your left-hand rule, all right, if it's coming out of the page, positive charge will go down, which means an electron will go up. Okay, and that would be that. Now, in order to prevent that electron from going up, if I apply an electric field to this, I have to pull that electron down, and I can do that by applying two plates, a positively charged plate on the bottom and a negatively charged plate on the top, and then the electron will be pulled down and pushed up. And for it to go straight through, the electric field strength, the force due to the electric field strength, has to be equal to the magnetic force, and then they'll cancel out. All right, and then this could lead us to some interesting questions that we're going to do in atomic physics. And in the last question, for DC motors, which I asked you guys to do some research on, a lot of you on the exam drew induction motors, which I can see that you Googled it, okay? But when we're talking about simple DC motors, you usually have a diagram that looks like this, where you have a magnetic north pole, a magnetic south pole that's permanent inside of the motor. And then you have something known as an armature that has a wire with a current going through it. Now, if I have my current, this is positive, negative, my current is flowing in that direction. What would end up happening is if I use my left-hand rule, this wire where the current is going up is going to experience a force pushing it down. And this wire where the current is going that way is going to experience a force pushing up. Those forces are going to create torque, causing the motor to turn counterclockwise. Now, in order for it to keep momentum, as soon as that wire turns halfway, okay, it cuts off the current so that the momentum keeps going, and then it turns the current on again. So it kind of pulses the current through the armature to keep that motor spinning in a counterclockwise circle. All right, and that's it. We're going to be applying this for HL in the next section for higher level electricity. And for SL, we're going to be doing this in atomic physics.